Oh, that's the good stuff. All right. So team formation form is live. You can find it either in the submissions category. This is where I'm going to put documentation for each phase, but I'll also put it wherever it makes sense on the course website. So this is where you really need that information, is right on the last day to form teams. Go to the team formation team. Hopefully I'm logged in. Oh, you know what? I'm going to do this just because I want to show the form. So you have two options here. Either you formed a team with 4 members, and you click this and go input your teammates. Super simple form. I probably don't have to explain this, but and then fill out your 3 teammates. The form automatically collects your email address, so you don't have to tell me who you are. Just tell me who the other 3 people are. You only need 1 submission per team, but if you submit multiple, if all 4 teammates submit the form, that's fine too. And actually, I recommend that just to make sure that your teammate didn't do anything silly. I've had cases in the past where somebody thought they were on a team, and then when the form was submitted, they were not on that team, and then I put them on a random team, and, well, they had a bad time. So it's fine if you submit. If I get 4 submissions for every team, that's fine. I know what to do with that. I can handle that. If you don't have a team or you don't want to form a team, I recommend going to either Discord or the Piazza posts. Try to find teammates. Try to find teammates who want to work in the same language as you. Would probably be the best way to do it in this course. Or if you have an idea for an app that you want to build, is always a good idea of forming a team around that. I usually discourage. I know you're going to do it anyway, but I usually discourage. I say this just so I can say I told you so. Discourage just forming a group with your friends, especially if they don't have the same app ideas or the same languages. Like, it's a good way to put tension on a friendship. It's not the best thing, but I understand you're going to do it anyway. But just be cautious of the dangers of that. If you're friends because you've already worked on a team in a previous semester, go for it. Like that's perfect. If you don't want to form a team, you don't want to go in those chat channels or whatever, you just want to be placed on a random team, just random team, next. That submits the form. That's the end of the form. That's all you have to do. Again, this will collect your email address. Make sure you're logged in with your buffalo.edu email address. If you're not, it'll say you don't have access to the form. Switch to your buffalo.edu address and then go to the form. If you want to be placed in a random team, that's all the action you have to take next, and then submit. I'm not going to submit because I don't want clutter in the data on the back end. So by next Friday, and ideally you should already be trying to form your teams. So get on that. If you don't submit this form by this date, then on Saturday I'm going to go through all the results. If you don't submit the form by then, you're just going to get a random team. And don't be one of those people who chose a team but didn't submit the form, gets put on a random team, the team gets split up, and then emails me after I assign teams and says, oh, but we were already a team. That frustrates me. It happens every time. It's just, please don't be that person, because I'm going to put you on a random team and you're not going to like it. Unless by pure chance your team gets randomly selected. Okay, enough of that, enough logistics. Let's go to HTTP introduction. Actually, I'll pause for a second for questions. Oops, Mike, ignore that, Mike. I clicked the wrong thing. This is what I want to click. I'll pause a second. Yeah, for free to. And when I mention those couple of cautions that I just gave, a lot of that comes from 442. Now, this class hasn't been around long enough to really see all the issues, but in 442, at least every semester, there's at least one issue with a team. So I like giving those warnings out just because I can give you a heads up. It's not a deadline you want to miss. Like, there's no points attached to that deadline, but it's definitely not one you want to miss because it can ruin your whole semester. Safest login, the Duo. As someone who is not, like, I'm not addicted to my phone, so I don't always have my phone on me. Being like that, Duo just frustrates me. Just disrupts my workflow all the time. I walk around the house and look for my phone. Usually I just don't. And whatever I was trying to accomplish, I just do something else. Not usually, but sometimes. But if you don't have all 4 yet, if you So I don't really want to advertise this too much, but if you have like 3 team members, I can't guarantee what I'll do. Really try to find a fourth and then submit, and then there's no questions. If you only have 3, you can submit the form and try to see what I'll say. If your 4th member, you say, we don't have a 4th member. The reason I don't like that is I don't like putting a random person in a group of 3, because it tends to be the group of 3 is a clique, and they're really close, and they've been talking, and then you have this random person who gets added, and they can feel left out. So I really don't like doing that. So if you submit like that, I might break up your team. You might be at my mercy there. But if you find a 4th, then you don't have to worry about it. When's the deadline for choosing a team? I just showed that. Next Friday. It's on the course schedule. Yeah, and the reason it's the end of week 2 is week 3, your team meetings start. And week 3, when you have those first meetings, I'll talk about it when we get closer to that. But your first meeting should be, trying to come up with the project ideas, talk about the course. Hell, if you just form a study group and start talking about the homeworks, that's fine too. Since there's not much you can do on the project quite yet. But you can start brainstorming and getting ideas for it. But I do want to know, you'll submit the team meeting form after each meeting starting week 3. And I need to see those form submissions just to know that you have been meeting, that you are thinking about the project and working on it. To make sure that you're on track with that you're not doing the whole thing last week of class. Yeah, just ask, Goozy Hoozy. Just ask, however you talk to fellow students. The teams have to be teams of 4. Have to. No exceptions on that. The only exception is if somebody resigns the course, you'll become a group of 3. But there are 120 enrolled. I'm not allowing groups of 5, and I need a max of 30 teams. Those are my constraints that I'm working under. Make a fellow kids meme. Yeah, that'd be the perfect way, actually. I guarantee, well, I don't, maybe not guarantee, but if you go into the Discord and say, hello, fellow kids, would you like to form a team with me? You'll probably get 3 takers. Hey, CSE review sessions, what's up? Okay. A lot of these are not questions about team formation anymore, so let's go. Let's do this. So, where have we come from? Well, we only had 1 lecture, but we covered 3 topics in that 1 lecture. Pretty quickly, we ripped through the physical internet, IP, and TCP. So we have the physical internet. We've literally, as a species, wrapped the planet in cables, connected those cables with routers, and now we can communicate bits of information anywhere on the planet. Cool, but how do we, that's just electricity and light that we're sharing. How do we organize that a bit? The Internet Protocol came in and said, okay, let's use things like IP addresses, let's use packet modulation, and now we can have a little bit of structure to those 1s and 0s that we're sending over these cables, but it's unreliable. So we added TCP on top of that and said within these IP packets, the information contained in those packets and the payload, we're going to use another protocol called TCP, which is going to give us reliable communication by using things like port numbers, by using sequence numbers, by establishing a connection, and then communicating a little bit of meta information about that so we can make sure that we eventually get all of the data, that the receiver gets all the data that we're transmitting to them. Even though it is the internet is fundamentally unreliable, TCP is going to make it a reliable connection. So great, we can effectively send information to anyone who's connected to the internet. Now, what kind of information do we want to send? And that's where HTTP is going to come in. It's going to give us more structure to the information that we send over the internet. And specifically, we'll use this to build web apps, of course, because that's the name of the course. So our packet structure is looking like this. We have a lot of headers. We'll have one big packet that's being sent over the internet. And the routers of the internet are going to look at the top of this, the IP headers, and figure out how to route this thing through the internet. Once this packet reaches its destination, the receiving machine is going to rip off these IP headers. It doesn't need the IP headers. That was just for the routers. And it's going to read these TCP headers and figure out which process this is going to go to. Your OS, at the OS level, it's going to read this header, figure out which port number. It's going to do all the sequence numbers and reassemble these TCP messages, and then send it to the process that's currently reserving that port number, that TCP port number. And then your OS is going to send that information. It's going to the process. The process is going to peel off the TCP headers because it doesn't need that information. Then it's going to read the HTTP headers and also the content of that if there's content attached to this HTTP message. So this is where we're going to start in the course. We're going to assume IP and TCP work as intended. And when our process, when you run your code, when you run your server, your program, that's going to be the process that the operating system sends the result of the TCP, stitching together these TCP sequence numbers and packets. That's what we're going to end up getting. So we have a reliable connection, and we know that when we send our HTTP requests and responses, that IP and TCP are going to work. Our information is going to be sent. We can just assume that that's reliable. We're going to receive information reliably. We start right here. This is where the course starts. This is where modern networking concepts works. This is where that lives, and a bunch of other protocols. You'll talk about UDP and I don't remember the other protocols off the top of my head, but a lot of other fun stuff you'll learn in that class. But we start here and go down. We're going to talk about this stuff for the majority of this semester. It's a lot of HTTP. Can you run a web server on UDP? I mean, technically you can, but it won't really work. You certainly shouldn't, because it won't really work. Because once you have a packet dropped, if you're missing a packet that's part of an HTTP request, you might not be able to handle that request because you'll be missing key information. UDP is really only used for a few different purposes. Live chat, live video calls. We'll use UDP. Actually, I'm not even positive what Zoom uses, if Zoom uses UDP. But Zoom should probably use UDP. Because it's only effective when you have information that's being transmitted, that if you drop a packet, sending the resend request like TCP does and saying, hey, can you give me packet 5? I missed that packet. The time for that resend request, if by the time you actually get that dropped packet, you don't want that information anymore, which is true with a video call or a Zoom, like streaming like that, then you would use UDP, because if you drop a packet, you don't want to go back to that packet. It doesn't make sense to go back, fill in those few frames of that video, and then go forward. So it's very limited applications. Even Twitch, like what you're watching me on right now, this is TCP, because you want the entire video. If you miss a few packets, you get buffering, and then your video is just a few seconds behind live after that, and then you're just a little behind unless you hit a refresh and get live again. But if you're communicating two-way with somebody through a video chat, you don't want to be 2 seconds behind live, because then you get a lot of miscommunication at that point. You're responding to something that someone said 2 seconds ago. That's just a pain. So UDP is pretty limited in its uses, but where it is useful, it's very powerful, very useful. All right. A little sidetracked, but good stuff. Because I clicked the next slide. Okay, so here's where we start, is HTTP, and I really won't talk about IP or TCP for the rest of the semester. We're just going to assume we pull in a library that does TCP for you in whatever language you choose, and then we're going to start building HTTP. So this is where the content that you're responsible for, that you'll be coding in your assignments, is going to start with HTTP. How do I access the class Discord to make a group? Go to the course website. Right at the top, I have some links. One of them is Discord. Check that out. You have to create an account and then go to the CSE 312 channel. And it's just one open channel for the course. Just say, hey, anyone looking for a group, and give your sales pitch or post a meme, whatever you want to do to try to get a group interested. Or one of these groups of 3 that's looking for a 4th. They probably already posted in there. You can just respond to them. Would probably be better. All right. So HTTP is an application layer protocol, meaning the OS. When I say the OS gives that data to the process, that process, which is our application and our purposes, our application is going to work with this protocol. Actually, our code that we write, or if you use libraries, of course, you're not explicitly writing it, but our code, our program, software is going to handle this. Not that the OS isn't software, but you know what? Let me stop that rabbit hole before I get too deep. So HTTP, this is what we're going to handle. And I already said all that. I got ahead of my slide. And today we're going to do just a quick overview. I won't get too in depth with the details of HTTP today. Trust me, we have the rest of the semester to do that. We'll keep adding new features onto HTTP. And the next 2 lectures are dedicated to HTTP as well. But today I want to give a good overview of a lot of the different pieces of structure around HTTP. So HTTP is usually used, at least in our context for this class, is going to be a browser connecting to a web server. Instead of browser, you can replace that with an app, a mobile app, or whatever. But it's going to be some TCP client. I'll always say browser, but you can replace that with what you want. Connecting to a web server. HTTP is a protocol. I mentioned this last time, and I'll probably mention this quite a few more times throughout the semester. But a protocol is just an agreed upon set of rules that both sides of communication will agree upon. So in our case, the browser and the web server both agree, hey, we're going to speak this HTTP protocol. So if you put information in this order with this exact format, I'm going to write code to parse that exact format to get the information that you're asking for out of that request. And then I can, as long as you agree on that format and I agree on that format, you write code to send in that format, I write code to parse that format. We can effectively communicate. But HTTP, it's just bytes, just like we saw with HTTP, IP. It's just a way to organize bytes of information, but we're going to work with ways to organize that. HTTP is going to define how that information is organized. And with HTTP, we do receive bytes, but we're going to immediately translate that into ASCII and then parse this HTTP, the headers, as ASCII text. So it's a lot of string parsing we're going to be doing at this point. And no, that wasn't a misspeak. It's not UTF-8 in the HTTP headers. We can only assume that they're proper ASCII characters in HTTP. So if you want to send something in an HTTP header that's not ASCII, you should base64 encode it and then send it over and make sure that the server knows, everybody's in agreement that, hey, this is encoded, decode it, get the bytes, then process that information. Usually we don't do that. Usually we'll talk about it throughout the whole semester. Usually, actually, I might as well say it. The body of the request can be whatever protocol, UTF-8, raw bytes, images. It can be whatever. But the headers of the HTTP have to be ASCII only. Can we run a... Oh, I read that a while ago. Didn't I? Yeah, the browser is the client. Yep. So the browser is going to be, fundamentally, like underneath the hood, a browser is a TCP client. And then the code of the browser speaks HTTP. And then the browser does tons of other stuff on top of that. But fundamentally, the first thing that any browser has to have is TCP client code. It's a desktop GUI with a TCP client that'll make TCP connections to the websites that we request. So HTTP is a request response protocol. The client is going to make a request to the server, and the server is going to respond with a response. So HTTP request, HTTP response. We'll talk about these in depth the whole semester. If you've done some web development, if you've used a framework, you've probably seen request response. That's probably the name of classes, the names of variables in the examples in the documentation. You've probably seen request response before. This is very fundamental to HTTP. It's a request response protocol. I request information from the server responds with a response, and I get that response when I make a request. So example, if you're on Twitter, you want to get the latest tweets for a specific user, you send an HTTP request to Twitter, And then Twitter server responds with an HTTP response containing those tweets, the information in those tweets. A request may trigger more requests. So if I'm just going to show this on the next slide, actually. I'll go back to that one. If a browser, an HTTP client makes a request for an HTML, this is usually when you go to a website. This is almost always the flow, the sequence of events. Make a request for the base HTML of that website. The server gets that HTTP request, responds with an HTTP response containing the HTML of their homepage. That HTML is going to have, in most cases, for the modern internet, usually a lot of separate requests that need to be made. There might be embedded images, there might be CSS and JavaScript, any other content that's needed to render that page, those are all going to have to be subsequent requests. Since this is just a request response model, there's really no other way we can, I shouldn't say that because, but we get the HTML, our browser parses through the HTML, looks for any other requests that need to be made, makes requests for all of those extra resources in parallel, just sends requests for all of them as it's parsing the HTML, and the web server responds to each one of those requests with the specific content requested. So there'll be an HTTP request for each image, for each CSS file, for each JavaScript, and a browser might be making requests to other servers as well. If you embed an image, if you've ever made a web page for like $1.99 or something, you want to embed an image on your page, and you just find an image online and cut and paste the entire URL into your page, then the browser is going to visit your page, get the HTML, see that URL for the image, and then make a request to another server, whatever server is hosting that image, and get that and then add that image to your website since you're not hosting that image directly. So you can have multiple requests for a single page. And then once all of the data is in, the browser is going to take all of that content and render it all on the page to you. And usually render as it's doing this. Browsers are really phenomenal pieces of software these days. They have so much optimization in them. They're doing everything in parallel to make sure those pages load quickly. So a web server is software that speaks HTTP. We're going to code our web servers to be able to speak this protocol. So when it gets an HTTP request, it can respond properly in a way that the browser can read that response and make our web apps work. We have terminology you've heard me say already, so let's clearly define these. Front end and back end. The front end of a website is anything that runs in your browser. You connect to a web server. The server sends all this HTML, CSS, JavaScript, images, anything that the client needs to be able to view that web page. That's the front end of the server. So if somebody says, or the front end of the web app. So if somebody says they're a front end developer, that means they're messing around with mostly JavaScript. Probably working with a JavaScript framework to be able to make pretty pages, make the buttons interactive, make things flashy, whatever they're doing. That's what they're working on. The back end is everything that's running on the server, and this is functionality that the client doesn't have access to. It's all going to run on the server in some data warehouse somewhere, in some data center. That's all the back end. Everything that's behind the scenes, any database access, the HTTP handling, the parsing, handling passwords, all that stuff is going to be on the back end, which is never sent over the network to the client. Our course will focus on the back end. We're going to be working on this web server and not so much the front end. We'll do very, very little front end stuff in this course. So an HTTP request, there are different types of requests. And these are kind of made up, to be completely honest. It took me a while to really finally realize that, but these are kind of made up. But I guess everything is, so, I guess it's no different than anything else. We'll be working with two different types of requests, GET and POST. I won't talk about the other types of requests in this course. Get is when we want to get information from a server, and post is when we want to post information to a server. The only difference between these is these letters. If a request has these letters GET in it, then it's a GET request. And this really only helps, besides some optimization that, depending on what software you're using, might be able to make. Besides that, the only difference is these letters. When I send a GET request, that tells a human user that, hey, this request is intended to be able to get information from the server. So if I code my server and I say I'm going to react to this GET request for this path, I'm basically telling anyone who's coding a client for this site that, hey, the point of this path is to get information from me. If I make a post request, if I have my web server react to a post request, and I say, hey, my server, my API or whatever has this post request, it means that we're expecting information to be sent. But there's nothing stopping you from using a GET request as a post request except convention, and absolutely you should not do that. You should stick to these, but there's no real magic. Like we'll have some post requests in this semester that could be relabeled as put requests by functionality. They'll function as a put request, but it's not wrong to make them a post request if we're sending information. But a put is strictly just sending information to a server or deleting information for delete. Both of those could either be GET or post. But I won't go too far into that. We'll work on GET and post, and we'll use them as they're specified, either getting information or posting information. Doesn't post have the possibility of storing state in the server? We can do that with a GET request, though. We can store that in a GET. So we can have a GET request that sends information to a server. We can have a GET request with a body. There's nothing stopping us from that as long as we code that in the front and back end of our site. It's horrible convention. You should label that as a post because it's acting as a post. But you technically could. It's probably something I shouldn't even talk about because it's such horrible convention. But even with a GET request, using it properly, you could store state in a GET request. Again, not the best idea. But that one you could actually do it without violating much convention. So a GET request, this is whenever you're requesting information from a server. Every time you click a link, every time you type in a URL in your browser, that's going to make a GET request. So if I type in google.com, that's going to make a GET request to google.com. And then the Google server is going to respond with whatever it's going to respond with. It's HTML. I'm going to parse the HTML, make a bunch of requests for all the other content, and then get all that content from the server. So any HTML, all the static content, which we call static content that I'm not interacting with the server besides just downloading stuff from the server, that's all going to be GET requests. Whenever I want to send information, so whenever you're filling out a form, in most cases, some forms will use GET requests. They can use GET requests. It's perfectly legal. Without breaking convention, like I was talking about before, they can legitimately be GET requests. But a post request is going to have a body and send information to a server. So whenever you're filling out a form, whenever you're uploading information, uploading an image, that's most typically going to be a post request. Unless it's a very simple form, it really should be a post request. Even simple forms, I'd argue, just make it a post. Make it proper. Delete information from a... Oh, yeah, that should be from. Yeah, good call. Good catch. Yeah, from a server. So if you... if I'm... This isn't the best example, but I'm blanking on a better one. If you post a chat in, a text chat in an app, and you're like, oh crap, I didn't want to do that, and then you delete it, that could be a delete request. Say, hey, that information, I want that deleted from your server. That's a bad example because the server, in most cases, isn't actually going to delete that. It's just going to mark it as deleted and then not send it to other users, but still keep it in its database. So it's not an exact example. But yeah, it's when the server's storing some information, you want that information deleted. So the URL is how we're going to access information pretty universally, pretty uniformly. We also use it for the internet, but it can be used outside of the internet and outside of networking. A URL identifies a specific piece of information or a specific resource, and it's going to follow this structure. So one of the first things we have to do is know this structure and be able to parse this apart. This has multiple parts. The protocol. What protocol are we using to access some information? For our purposes, mostly this is going to be HTTP. At the end of the semester, we will dabble into HTTPS. This could be other protocols, any other protocol that you want, even non-networking protocols. If you have an HTML file on your machine and you just open it up in your browser, you're not using any protocols to do that. You're not accessing information from a web server via HTTP. You're just opening a file using the file protocol. And if you do that and look in your browser, the URL will actually start with file. That will be the protocol. You're just opening a file that's on your hard drive. Chat is a post request. Depends what you're talking about too. So I mean, we're just on day one of real juicy content here. But like the chat that you're sending right now is over a WebSocket. Twitch uses WebSockets for its chat. But chat would be a post request if it's not WebSockets or some other technology. All right, so protocol, mostly HTTP for our purposes. In the homework, I should say, and in the project, the code that you write this semester. And then the host, this is what web server are you referring to? Call it by name or by its IP address. If you call it by name, there's a DNS lookup that gets the IP address, but it's what is the IP address for the server that you're connecting to, or whatever you're connecting to, your hard drive, a web server, an FTP server, whatever you're connecting to, what machine is this being connected to? The port number, the TCP port number, which port are we connecting to on that machine? So machine, we can think of this as which machine are you connecting to, which machine on the internet, which process on that machine are you connecting to. This defaults to 80 or 443 for using HTTP or HTTPS respectively. For development purposes, we usually use 8,000. I'll use 8,000 like in the homework, so I'll force you to use 8,000. At least for submission. When you submit, use 8,000. And 8080 is common. There are a few common ports, 3,000, that we use for development purposes, which are ports that aren't used for anything else. So when we're testing our apps, we like to use those ports because it's not going to interfere with other processes, except our other development processes that we may be using. And finally, the path. Which specific resource are you requesting? Which protocol are we using? Which machine are we connected to? Which process on that machine? And what resource of that process do you want to retrieve? So that's how we can get a specific piece of information from wherever, either our own machine, a machine connected to the internet, for our purposes, a web server running somewhere, anywhere. Next, we have some optional parameters that we can put in the URL. First, the query string. This is something we'll talk about in, a couple of weeks. The query string, but this is mostly what you need to know about it, honestly. I could just cover it right here, I guess. The query string is optional. If you have a query string, there has to be a question mark in your URL, which implies that question mark is not allowed anywhere else in the URL. Your path cannot contain a question mark. But if there's a question mark, that indicates the start of a query string, which is a set of key value pairs with extra information for the web server. So if we want to make a Google search for web development, Google search uses a query string for this. So if you make a Google search, you can look at your URL after the search. You'll have a Q for query, and then the syntax for a query string is equals, and then whatever that key, whatever value is stored at that key. If we want multiple key value pairs, separate them by ampersands. So if I want to make a query, an image query for web development, this is DuckDuckGo syntax. That's their agreed upon protocol that their server understands to be able to send these key value pairs in the query string. I think that's and fragment's going to start with the hashtag. So question mark, hashtag or pound sign if you're old like me, ampersand, and a couple others. I think equal sign, slashes for sure, colons. These are all banned. They all have special meaning in a URL, so these are all banned anywhere else. You can't have a path that contains any of those characters because those characters mean something. And to parse a URL, if there's a pound sign in your path, it's going to think that's a fragment. It's going to make it impossible to parse these things. So next, the fragment. This is usually used just for navigation, but it's an extra piece of information, just a single piece, not key value stores, not data structures or anything, but a single piece of information, which usually tells us where exactly on this page should we navigate. So, for example, if you go to the Wikipedia article for URL or URI, it'll take you to that page as you would expect. Of course, you've done that your whole life. If you add the fragment to say definition, this is going to load this page and then automatically scroll to the definition part of that page. You can do this. I do this sometimes with PDFs as well. If I have slides, if I have 50 slides in a slide deck and I'm answering a question or something and I want to point a student to a specific slide, you can use this pound sign and then the page number of that slide. So when they click that link, it scrolls directly to the slide that I'm talking about. Is a handy way to do this. PDFs, browsers will open PDFs based on this fragment to that specific page that you request. I forget the exact syntax for that. I think it's like page 2 would scroll to page 2. Or maybe just the number. I don't remember. See you, King Assassin. Take care. So let's get into HTTP requests. I got 10 minutes, right? Okay. We got this. So let's talk about the actual structure of an HTTP request once we get this on our server. So from the URL, the protocol, we're going to assume that's HTTP. The host and the port number, well, since we already have this information, we know that the host and port number, that already worked because we got the information. So this must have been routed through the internet based on our host. Our OS must have sent it to the appropriate process because we're getting the information. So that information we don't need anymore. It's already been used. But starting with the path, which will include any query string and fragment in it. In my examples right now, I don't talk about those. We'll address query strings later and parse those things. But the path is going to be everything that's after. It'll be more than just the path. I should say path query string fragment. But it'll be everything that's after the port number. We're going to get in the HTTP request. That part of the URL is going to still be relevant because our process has to handle that part of the information. So a request line is going to consist. A request is going to consist of 3 parts. A request line, which is going to give us, most importantly, the path that's being requested, like I was just explaining. The header fields. And then an optional body in the request, which typically a post request will have a body, a GET request will not have a body, is the convention that we follow. So the request line itself has 3 parts, and this is where we start talking about formatting and string parsing. So when you have your TCP socket set up and a browser sends you a request, you're going to get a request following this format, and you got to do string parsing, parse this stuff to get the information that you need out of it. So the very first line is always going to be the request line. This has 3 pieces of information separated by spaces. So when you read the first line, you can look for these 2 spaces. I like to do read the line and then do dot split on space and get these 3 pieces of information. The first piece of information is the type of request, GET or POST for our purposes. The second piece of information is going to be the path with any query string and fragment. And the third piece of information is the version of HTTP. We're always going to use HTTP 1.1 in this course, and you can assume that that's accurate. You can assume that that the protocol is HTTP 1.1. So if you don't want to read this and you don't want to have all these conditionals in your code that says if HTTP version equals HTTP/1.1, then handle the request, else return 404 or whatever. You don't have to do that. You can assume that this is correct. But you do have to look at the request type and the path. If you're expecting a post request and somebody to a specific path and somebody makes a GET request, you shouldn't handle that. You shouldn't respect that request, for example. You have to read the request method and the path. Next are the header fields, which is extra information about the request. And these are crucially important. We'll talk about all kinds of different header fields. This is extra information about the request. There can be any number of key value pairs as headers, and the key and value are separated by a colon and a space. So when you're parsing this, you read the first line, that's always the request line, and then read any number of headers to be able to get all the header information out of this HTTP request. And then if the request is a post request, you're going to have a body, and the body and the headers are separated by a blank line. So once you see a blank line in the request, that means you're done with the headers. That's the way that a request signifies, hey, no more headers, you're done reading headers. Next is either the end of the request or the body is about to start. And for headers, if there's information contained in the request, at a minimum, you need a content length header. This is going to tell the server how many bytes of information to read, how many bytes of information are contained in the body. This is very important for parsing. Whenever you get a post request, you'll read the content length, and then when you read this blank line, you know to read 48 bytes in this example. This GET request has no content length, so you know once you read a blank line, and every request will end in a blank line, or will have this blank line whether there's a body or not, rather. Once you read the blank line, then you know, okay, I never found a content length header, so that means this is the end of the request. So content length is very important to parse. Again, I'm doing an overview of HTTP today. We won't be parsing content length until homework 2. That's where you have to read content length. For homework 1, you'll have to write content length in your response. So you get an HTTP request, you parse through all that information, you parse through that ASCII, and then you're going to have to formulate your HTTP response. Whatever code runs in between, that's what your app actually does. The features you want to build, all the cool stuff you want to build that you want your app to do. And then when you're ready to send a response to the user, you have to formulate one of these HTTP responses. And in most cases, your response is going to contain a body. You're going to actually be responding with some information, except in some cases where you just need to say, you just need to give an acknowledgement back to the server. In most cases, you're going to be sending them information, your HTML, your CSS, your JavaScript, your images, your videos, whatever it may be. So in your HTTP response, we follow a very similar structure to an HTTP request in the sense, especially after the first line, but the first line is a little different. The response line is structured a little different than a request line. So the very first line in an HTTP response is going to follow this convention, 3 pieces of information separated by spaces, so kind of the same structure. But the first piece of information is the HTTP version. In our case, is always HTTP/1.1. So every HTTP response that your server sends has to start with these characters, HTTP, all in capitals, /1.1, every time, and then a space. After that, things can get different based on what information you're sending. If this is where we put the response code and the response text, where the response text is a human-readable representation of the response code. So for this example, we're saying, hey, everything went fine. Response code 200, everything's good, nothing to worry about here. We're going to have a body in this request. If for this example, we're sending some HTML to the user, so to the client. So we're going to have to add 2 extra headers. These 2 headers are going to be required when we're sending information in the body of a request. We want to specify the type of the content. In our case here, it's text, and that text represents HTML. And the content length, there are 152 bytes of information in the body of this request. And it's going to be important for the For the browser to be able to parse this, the browser is going to parse this just the way that we will parse a post request, and it's going to read the content length. Once they find a blank line, then the browser is going to read 152 bytes of information. And after 152 bytes of information are read, it's going to assume that that's the end of the response, and it's not going to read any more bytes. So if your content length is less than the actual amount of content you send, you're going to be missing some content when you load up the browser, which will be very painful when we're talking about images. If you're hosting an image and your content length is off by 1, depending on which format you're using for images, the image might not be able to be decoded, and you're going to have a completely broken image because you missed 1 byte of information. So very important to get the content length right. In HTML, if you're missing like the closing HTML tag, browsers are pretty forgiving about that. But if we're sending something that's encoded, very important to get that content length right. It's always important because, we're going to be looking for it during grading, but very important for usability as well if that's off. So the response code can be, there are a lot of different response codes, tons of codes that you can look up and see what you have to play with. The most common one that you're going to get when you're browsing the internet is 200 OK. Everything went fine. Everything's good here. Here's your information that you requested. The next is 301 moved permanently. We have, this is a redirect request. So, hey, this site doesn't really exist anymore. We move this site to this other URL. Go to this URL to get the information that you want. And not modified, this is for caching. If a resource hasn't changed since the last time it was requested, which will be the last request time will be in an HTTP header. If that resource hasn't changed since that last request time, you'll just get a 304 not modified, and you don't have to re-download that information. Saves network traffic, saves your bandwidth. These first 3 codes, you might get these a lot on the internet, but you'll never notice as a user because you'll just be looking at the page that you requested. So next we start getting into the error codes that the HTTP response codes that you've probably seen before. Forbidden, you don't have access, you tried to access something without logging in or whatever. Something you're not allowed to access. 404, infamous, the resource you requested just doesn't exist. We got nothing for you on that path. Try again, figure it out. And 500, the stuff of nightmares for web developers, internal server error. This means something on the server itself broke. That means the user requested something. The request was fine. There was nothing wrong with the request that the user made. But the server broke. Something's wrong with the server. This is where web developers can get calls up at midnight. Hey, we got a fire. We need you to put this out. There's an error with the code. We got to hot fix this and push it to production. Scary stuff. Every time I see a 500 error, chill goes down my spine. It means you as the developer messed something up. In most cases, some cases, like some of you might have seen 500 errors on Autolab where the server just got something that wasn't expected, but it's because you were, I guess in not all cases. Some of those 500 errors we should get rid of. But anyway, so HTTP, I only got one slide on this. This will be a lot of homework 5. We'll talk about this in depth. HTTP is a stateless protocol, meaning every request is handled in isolation. So there is no sense of state in HTTP. So if we want some state, we're going to use things like cookies. So if you log into a site, you're going to get a token in a cookie, an authentication token, and then each time you make a subsequent request, that cookie is going to be sent to the site. The server is going to verify that you have logged in sometime in the past, even though it doesn't remember that HTTP request where you logged in, where you sent your username and password. It's going to read that token, verify that you have logged in, and then serve you the content that you want. So you don't have to type your username and password on every single HTTP request that you ever send. So we use cookies and tokens. I'll let you download the slides and look at it because I want to get to at least one example. And we have negative time. So if I go to the network tab in my browser, we can see all these HTTP requests. So I can see the HTTP request that's made when I visit cc312.com. It's a GET request for the root path using HTTP 1.0 or 1.1. The host name cc312.com. This is usually attached to requests. Some extra information, stuff about caching and connection. The caching, which made my images at the top look all funky if you've ever visited the page before, until you delete your cache. If any of you saw that, I think only a couple of you saw that before I fixed it. User agent, some extra information about this request. And then since the response, which I don't think you can, I don't recall a way, response. Yeah, I can see the headers but not the content. So the response, I get HTTP 1.1, 200, okay, everything's fine. Here's the information that you requested. Some meta information about this, and then importantly, the content type. And the content, oh my goodness, it was going to be the last thing I say too, and it's not here. Where is content length? Okay, well, content length should be there. And then once that HTML is parsed, that has requests for all kinds of other information. A lot of subsequent HTTP requests are made. All HTTP 1.1, all 200, everything's working fine. And just to wrap this up, view source. Give me a content length. So content length. This is textual information representing a cascading style sheet, and it has this many bytes of information contained in it.